Hello, my name is John Parks. I'm a senior at Maryknoll High School in Honolulu, Hawaii, and my presentation is Construction of the World Recycled Thermoplastics. So today I split up my presentation into 5 sections: the intro, methods, results, discussion, and so living in Hawaii, I'm no stranger to the effects of plastic pollution. Plastic litters our beaches, it kills our wildlife, and it ends up in every level of our food chains. Living on an island my whole life, it has opened my eyes to the incredible amounts of plastic debris littering our world and floating around the ocean, but it has also given me a unique perspective on how to...
Can you move the mic a little closer for the recording?
Yeah. I've learned about many of the impressive material properties of plastic at a young age. I've been always really fascinated and always wanting to find a way to deal with this problem and find a use for this ubiquitous resource that's everywhere. At some point in time, I turned to YouTube and I saw a couple of videos from Africa, Colombia, and Russia on using waste trash and mixing it with sand and creating housing tiles, paving tiles, roofing tiles, and bricks for construction at a very low cost. And around a year ago, I started doing research on habitation units on Mars, and I was really captivated. Inside my head, something clicked, and I remembered the plastic sand tiles that I had seen, and I wanted to pursue further. So I wondered if it would be possible to use the mountains of plastic waste we already have here on Earth, mixed with Martian regolith, to create a super durable, insulating, radiation-resistant, multi-purpose construction material for Mars habitation. I formulated my hypothesis from here, which was recyclable thermoplastics, when melted down and combined with Mars regolith, could be extruded to make a useful construction material while generating public support for Mars habitation. And recyclable thermoplastics are durable, insulating, radiation-resistant, and plentiful. Next section is going to be the methods. So the equipment I used included a mechanical shredder, a conventional oven, a conventional freezer, safety equipment like a respirator, eye and hand protection when I was working with the molten plastic, a compound pendulum for testing brittleness, and a hammer and nail for impact testing. I ordered a 2-kilogram sample of MMS2 enhanced Mars regolith from the Martian Garden, and I chose this simulant because it's very similar chemically to the composition of Mars regolith. And even though there were other less expensive, less accurate simulants I could have used, I ended up using this simulant because I knew I'd be melting down the plastics and I wanted to have the most accurate results to the Mars regolith that I could. So after purchasing the regolith simulant, I collected samples of commonly found household recyclable disposable plastics outlined in the table here. I chose both high-density polyethylene and polypropylene because they make up nearly 2/3 of all the waste plastic in the planet. Using a conventional toaster oven in my garage, I melted down the high-density polyethylene and polypropylene. And as you can see in this first photo, I have the shredded plastic, and it's actually, that one is mixed with regolith. And then in this photo, it's mid-melt. It's been around 10 minutes inside an oven at 350 degrees. And the pieces of plastic that are most close to the heating element had started to melt. By around an hour, it had become completely molten, and the actual temperature of the plastic was 300 to 350 degrees Fahrenheit. And after that, I would put it inside of a metal tray, and I would compress it, and then leave it in the freezer at 0 degrees to cure for 72 hours. So, as this slide illustrates, I prepared 12 60-gram samples at the following designated proportions of recyclable plastic to regolith simulant: 25 to 75, 50 to 50, and then thirds being 33, 33, 33%, as well as a 50, 25, 25, and a 37.5, 37.5, 25. Samples of 100% polyethylene, 100% polypropylene, 50% polyethylene polypropylene mix, and 100% regolith simulant were also used and included as controls. Now to the results. So, following the mixing of the assigned samples at their designated proportions and identical weights. Samples were placed in the freezer and frozen at a temperature of 0 degrees or negative 17.8 degrees Celsius for 72 hours or 3 days. After the freezing, I took all the samples out individually and tested them for brittleness at 0 degrees as well as impact resistance at 0 degrees. I also tested the conductivity of each of them, making sure that they were still, or checking to see that they were still insulators after these tests. The types of plastic that I used were specifically polypropylene and high-density polyethylene, found from commonly sourced household plastic waste, like milk jugs, bottle caps, plastic planters for gardens. And in this clip, you can see this is the compound. It's in my garage, but there's a compound pendulum that I used that sits 18 inches high and has a 6.5 pound arm, and I have a vice grip holding the sample. Here it goes. So for this first test, the sample fails and it breaks. And in these ones, the sample does not fail and it passed the test. I ran this test 3 times on each sample, and if it cracked by the end, it failed, and if it didn't, it passed. I also did for the stress test with the impact. I took a hammer and nail, and I just very simply raised my arm up with the hammer and just let it fall right on the nail. And I did the same thing 3 times. If it broke by the 3rd time, it failed. If it didn't, it passed. The mass of the hammer was a 16-ounce curved head, and I used a 20D nail, which is 4 inches long. And then here's the example of it being hit. In this test, this is actually 100% polypropylene, and this was the first hit. It actually went 2 hits, and on the 3rd it broke. I think that's because of the brittleness of polypropylene, and because it's more of it's one of the stronger plastics, but it's not nearly as flexible, it's more rigid. I also tested for conductivity with a multimeter. So for my results, as you can see, the first 4 samples all passed. And the interesting thing about that is they all contained mixtures of high-density polyethylene. What surprised me was 100% polypropylene mixture from everything I had read. I had read that it was a very strong plastic, yet it failed the impact test at 0 degrees. Another interesting thing to me was when I mixed polypropylene and high-density polyethylene together, again, what I had read and from the available literature is that they were immiscible and would not form a strong sample when melted together. Yet during the testing, it didn't fail like a lot of the other regular polypropylene mixes did in the brittleness test, but it did have a large crack, so I assume it would not be nearly as strong. I also want to point out that the mix that surprised me the most was the one at the very bottom, which was 37.5% high-density polyethylene and polypropylene, or 75% plastic to 25% Mars regolith simulant, and it failed both tests, whereas the other one that was even distribution of the 3 samples passed both tests. So I want to point out that all of the 4 on the top that passed all contained high-density polyethylene, and the high-density polyethylene in this test performed just as well as a 50-50 mixture of regolith and high-density polyethylene, supporting the conclusion that milk jugs would be a great material for Mars. So the limitations that I encountered while doing this is I have a lack of lab space. I did this in my garage. I have a lack of equipment, like a hammer and nail for impact testing. I have temperature testing limitations because I can't get the temperatures in Hawaii that you have on Mars, because it's a lot colder there, and it's pretty hot in Hawaii right around this time. So I was only able to get down to 0 degrees Fahrenheit, whereas that's probably one of the hotter days on Mars. I also don't have an industrial extruder, so for all of the mixing of the molten plastic, I had to do it by hand wearing welding gloves, which was really, really hot. And led to a couple burns, but it wasn't that bad. I also have lack of access to a 3D printing lab where I could do larger scale 3D printing to test if the regolith mixture would be good at or would be suitable for printing even. I also use regolith simulant, not actual Martian soil, so there could be some differences there. And I also have a lack of time because I'm a high school senior and I have classes and varsity football. For the discussion. So I was able to achieve my experimental objectives of testing various proportional mixtures of regolith simulant to recyclable plastics for the various strength and conductivity properties under the circumstances that I had. And the results of the experiment support my hypothesis that recyclable thermoplastics, particularly HDPE combined with Mars regolith, could be extruded to make a useful construction material, while reducing waste and generating public support for Mars habitation. I recommend further research into the mixtures containing HDPE and regolith, as well as a 1:1:1 mixture of HDPE, polypropylene, and regolith. Given further time, I would really like to conduct further research on testing the effects of exposure and constant UV radiation on the mixed HDPE MMS2 samples that passed the test, particularly in situ, as the impact of UV radiation on Mars would be much greater than it would be here on Earth and would degrade the polymers much quicker. If there's any private company or government agency that would be willing to work with me on this, I am free to talk after this presentation. I'd be more than happy to do this and greatly appreciate your time. I also have interest in further understanding the logistics, financial realities, and societal impacts of transporting our waste, specifically plastic waste, off the world. Bringing me to my conclusion. While construction of habitat using in situ resources currently available on Mars is both plausible and currently being planned for future missions, the collection, transportation, and upcycling of ubiquitous and problematic sources of disposable plastics on Earth, so that they may be used as a practical and valuable sources of construction material on Mars, would not only help to bring societal action to helping to address the issue of plastic waste, but also galvanize public attention and interest in directly supporting human settlement of Mars through household contributions, including an online social plastics campaign, where voluntary households pay a fee for the collected and shipped recyclable plastics to be shredded, processed, and then sent either into as loose packing material between payload items to low Earth orbit or to Mars directly. I'm working on launching actually this social plastic campaign online by way of this talk. I'm inviting any interested partners to approach and meet with me to discuss working on this. And my hope is that the results of my garage-based experiments can contribute to an existing investigation into research in the preparation of human habitation units on Mars and elsewhere in the solar system. As I am a senior in my high school year, I'm hoping to be accepted into collegiate engineering programs so I can pursue a technical degree that will allow me to continue experimenting and working on this field in the future. So thank you guys for... my physics teacher, Dr. Eugene Gillian, Dr. Zuber and the Mars Society for allowing me to be here, and the Precious Plastic YouTube channel and community as a whole, who is dedicated to cleaning up the environment through recycling plastics, building your own machines to shred, extrude, and then compress and mold plastics. And then, any questions?
How did you pick your the temperature to mix the two components?
So the temperature that I chose was, I actually started out doing it around 300 degrees, but I have a time constraint, like...
Fahrenheit or Celsius?
For melting it?
For mixing the components.
Oh yeah, so I mixed it by literally putting the plastic in an oven and waiting until it was a liquid, and then slowly adding material and kneading it in like dough. So I had to get it hot enough for it to become a liquid, which was around 300 degrees.
Fahrenheit or Celsius?
Fahrenheit, sorry.
Fahrenheit. Is that above the pyrolysis temperature of any of the plastics you picked?
It is. That being said, the only reason I went above it is because of the time constraint. I found that when trying to do this at its melting point, it took a lot longer. I simply didn't have the time to do all of the samples like that. So that could be another factor, but I mean, other than that, it was pretty much just mixing it by hand.
So you know in an enclosed habitat, there's always a few melting plastic.
Yes.
So did you factor in the gas?
So
You're melting it?
that's actually a good point. I didn't factor that in, but what I did do is I made sure that while doing this, that all of the plastic was just one at a time. So I didn't have multiples that didn't cross-contaminate each other. So each of the samples was done individually. Sorry.
Yes, we're going to be developing on Mars a fuel manufacturing economy. What kind of plastics are most compatible with, systems that are set up to make basically oxygen and methane?
I can get back to you on that.
Oh, yeah, sorry. By the way, I think the answer is polyethylene.
Yeah, I
It's
think
actually
it is
a
too.
very
The polythene.
easy. It's a very easy thing to
It
make
is.
ethylene from methane
Yeah.
and oxygen.
And it's also a very big, it's not only easy, but it's very common and it's very safe to work with
Yes.
as a plastic.
Yes, I forget if you mentioned what was the ratio of the regolith sand to the plastic, let's say weight for weight, or
So
did you even vary that?
Yes, so all of the samples were 60 grams by weight, and I did 25% plastic to 75% regolith, as well as 75% regolith to 25% plastic, as well as a 50-50 mixture for all of the plastics individually. And then with all of those, I also did a 50-50 mix of the plastic to the regolith. So it would be like 12.5% polyethylene, 12.5% polypropylene, 75% regolith. So I tried to cover my bases for that.
By weight, you mixed them 50-50 by weight?
Yes,
or volume?
by weight.
By weight. I think that was the question.
Okay, sorry, by weight.
Maybe that wasn't.
So which of those three ratios do you think was the best?
I think that, well, from the results, from the data that I collected, what appeared to be the best mixtures were these 50-50 HDPE to regolith, because it contained the least amount of plastic and performed just as well as 100% HDPE. That being said, if we continue the test further, you could probably see failure earlier on the 50-50 sample, but from these tests specifically, it performed just as well as the pure plastic.
Yeah, so it's strong.
Yes. Which surprised me. I actually originally thought that all of the things that were combined with plastic would perform much worse. Because
Can you flip back to that chart where you had the results? Did you hear the box? Yeah.
So, the top results that didn't fail any of the tests were a 50-50 mix of HDPE to MMS2 regolith simulant, 100% HDPE, 75% HDPE to 25% MMS2 simulant, and a 1-to-1-to-1 ratio of polypropylene, high-density polyethylene, and MMS2 simulant.
Thank you so much, John.
Thank you.